Okay, this is where it gets exciting. So grab a piece of paper, and I want you to sketch this beam diagram. So you may need to pause this while you get your paper out. And while you are sketching, or after you have sketched, I want you to notice that this side is fixed. It's our little triangle right here. This side is on a roller bearing, so it would allow for expansion and contraction on this side. And we have a point source right here at 4,000 pounds, 6 feet from this end, and 14 feet from this end. We have the weight of the beam is 650 pounds per foot. It's 20 feet long, so we should be able to figure out the total weight of this beam if it's 650 pounds per 1 foot. So this should be drawn. Don't go on until you have this fully sketched out. Now that it is sketched, we can add a couple things to make this a free body diagram, and the free body diagram just shows all the forces. So we need to include this arrow, this Fy A. This is at point A, force in the y direction at point A, force in the y direction at point B, and the force in the x direction at point A. Remember, this is a fixed point, and so fixed points experience x forces. Rollers don't, because it can slide side to side and it's not feeling anything. All right, so as long as you have these drawn, these arrows indicated on here, you can move on, but make sure you have it drawn exactly like this before you move on. All right, here we go. Now we are going to calculate reaction forces. So don't write any of this stuff down yet. Let me just explain this. You need to use equilibrium equations to find the magnitude of the reaction forces. We want to find out the force on point A in the y direction and the force on point B in the y direction. First we're going to look at horizontal forces, and we assume that going to the right is positive. So in this case, we're going to say that our x force is 0 because we don't really have a point force. This point force is going straight down. There are no lateral forces on this. There's no force going kind of down at an angle like that. That is not there. So this actually is 0 to begin with. So that makes that easy. So this thing is just gone. So what I would like you to add to this drawing then, maybe just below it, is write the sum of the forces in the x direction is 0. So Fxa is 0. Now we got to figure out what Fya and Fyb is. So here we go. Now down below this diagram, I want you to start jotting some of these things down, but maybe wait until after I walk you through it. So vertical, we're going to assume that up is positive, and you have to make a declaration because it's important that we know which way we're talking. If this is positive, that means this is going to be a negative 4,000 right here because it's going down. So it's really important that you know that. So if the sum of the y forces has to be 0 because this beam, we don't want it to move or the whole building is going to collapse. So Fy at point A and at point B, if we add those together, remember they are positive because up is positive, and then we subtract the 4,000 pounds going down and the weight of the beam. And the weight of the beam is 650 pounds per foot times 20 feet, so that's why we have this here. And so we're going to subtract those. Now, what we can do then is we can move these to the other side over here. And so if we add 4,000 and we add the sum of these things, or the product of these, we get that on the other side. So they become positive. So the upward forces have to equal the downward forces. So you could start, I guess, you could start by writing it out that way too. So we have these two forces equal 4,000 plus 13,000. Again, 13,000 is the downward force, and that's 17,000. So let's show their little drawings here. They're showing that is the equivalent concentrated load, and that should be right in the middle, right here. That concentrated load of the beam is equivalent to being right in the center of this beam. So we need to know that that distance then is right in the middle. That distance is 10 feet from the edge, that a concentrated load. That's going to come into play later. So make sure you have this noted down, that Fya plus Fyb has to equal 17,000 pounds. Now we have to calculate the sum of the moments. So in this situation, what we're going to do is we're going to calculate it from point A. And you could do it from either point. It doesn't really matter. We're going to do this one from point A, though. And we're going to say that from point A, first of all, there would be no moment on Fya because it's not moving. There's no distance here. And we actually don't know this yet. That's the final answer. So what we do know, though, is that the force of y at point B, if we're going in this direction, and that's what we're saying is positive, going in this direction here, that this y force is a, we don't know the value, but it's 20 feet away. So we're going to do force times distance, because remember, moment is force times distance. So this FYB times 20 is a positive. So we're going to take that and get ready for it. Pretty great transition, huh? All right, so we're going to take this as a positive value times 20 feet, force times distance, and we're going to subtract, because it's going down, 4,000 pounds times, how far away is that? Looks like 6 feet. So we take 4,000 pounds times 6 feet, we subtract that, and we're also subtracting this 13,000 pounds, and we need to know that it's in the middle. And that's why I wrote that on the last one. That's always concentrated in the middle. So we subtract 13,000 pounds times 10 feet, because those are going the opposite direction. So we are adding this as a positive number, and we're subtracting these values. And then the Fy, because we're going to say this is going up, but it's zero distance. So this just goes away. That's just 0. And so if we sum all these forces, they have to equal 0. So let's take a look at the next step here. That was another good transition. All right, so we have 20 times F minus, when you multiply these together, 24,000 minus 130,000 plus 0 equals 0. So we're just finding the product of these. Now we can probably move this 24,000, 130,000 to the other side. Oh, it just peeked in there. We have 20 feet times FYB, and that equals 154,000. So now to just find FYB, we divide by 20. Let's see it expand. And we get, bounce, 7,700. So that is your answer, 7,700 pounds on this side, FYB. But that's not it. Remember, if we're pushing straight down with 17,000 pounds, and that was, remember in our first slide, 17,000 pounds, add these together. If 7,700 pounds is on this side, then how much is on this side? Well, let's find out. So now that we know FYB, we can use the previous equation to find FYA, and oops, here's the answer already. Let's watch it fade in. The sum of these is 17,000. FYB is 7,700. So FYA is 9,300. And that is what you're going to need to do when we do calculating reaction forces. And again, structural engineers absolutely have to know this and be able to do this, because if you have extremely heavy loads that you're trying to place on a structure, then you need to be able to calculate how much force is this thing going to need to withstand. It also helps with column loading, because then once this attaches to a girder or a column, then we can figure out how much load actually is applied to those columns and then to the footings. So your next step is going to be to do a few of these on your own. If you're still not really sure how to do it, I have a couple practice problems that I'm just going to walk through in the next video if you want to check that out before you do them on your own.